Hello everyone, and welcome to episode 5 of our video tutorial series where we dive deeper into the powerful features of the Building Generator tool for Unreal Engine 5. In this episode, we're taking things up a notch by introducing the Procedural Content Generation framework. We'll show you how easily PCG can be integrated with the Building Generator to automatically populate your levels with buildings and custom assets, saving you time and taking the heavy lifting out of environment creation. This workflow streamlines your entire level design process, making it faster, more efficient, and totally scalable. With PCG's procedural magic, you can generate unique, diverse, and visually rich environments with just a few clicks. But we're not stopping there. We'll also show how to combine the Building Generator with our Crossroad Generator for seamless urban layouts. And to top it off, we'll integrate high-quality assets from the Quixel Megascans library, giving your scenes that polished, cinematic feel all in just minutes. Let's get started. Let's start by setting up a level by adjusting some of the project settings. Go to the project settings and look for virtual texturing support, then make sure it's enabled for this project. Next, open the plugins window and in the search bar type PCG to find the Procedural Content Generation framework, and ensure that it's enabled as well. Since we'll also use the Crossroad Generator in this tutorial demonstration, enable the Geometry Script plugin too for full compatibility. Now, let's move on. First, create a new folder inside your content browser and name it PCG. Within that folder, create a PCG graph and give it a name like PCG_buildings or any label that matches your preferred naming conventions. Also, create a new blueprint actor and name it BP_street for this example setup. Open the blueprint and add a spline component to it for layout shaping. Then adjust the endpoint's location to something like 2000 units to stretch it out visibly in the level. Click on the BP_street root component and in the Details panel, search for tags, add a tag named Street so PCG can recognize it during runtime sampling. Compile and save everything neatly. Now, drag and drop the BP_street blueprint into your level and extend the spline visually. Also, drag the PCG graph actor into the level and expand its gizmo boundaries so it covers your spline actor completely. Open the PCG_buildings graph and start building it step by step. First, add a getActorData node. Set the filter to all world actors and input street into the actor tag field so the graph will target it correctly. Enable select multiple as well, in case you want to use more street splines later. After that, add a spline sampler node and connect it to the getActor node. Set the mode to distance and distance increment to 1500 units, for example. Enable debug mode to preview your sampled points in the editor window. If the points don't show up properly, go to the PCG graph actor in the level and change its scale mode to absolute to fix the visibility issue. One of the great things about PCG is that it has built-in support for spawning blueprint actors, which means we can directly use our custom Building Generator tool within the graph. This allows us to procedurally place fully functional building generators along our spline or across the landscape, giving us a lot of flexibility and control in designing dynamic environments with minimal manual effort. Now that you can see sample points, add a spawn actor node to spawn actual objects at each point. In the Template Actor class, select your BP_building generator blueprint as the object to spawn. You'll now see the building actors appear along the spline path. To simulate a street layout and eventually place an actual road instead of the spline, we need to offset the buildings to one side. Start by adding a transform points node before the spawn actor node and set a positive offset value like 1500 on the y-axis for both the min and max offset. This will shift the buildings to one side of the spline. Next, duplicate this setup and add another transform points node, this time using a negative offset like -1500, to place buildings on the opposite side. As a result, you'll get 2 rows of buildings flanking the spline, simulating a basic city street layout that can be easily expanded and customized through PCG. Now let's move on to the more interesting part, adapting this setup for other spline-based systems. Since we're using a spline actor, we can easily transfer this functionality to any actor that contains a spline component. In our case, we'll use the Crossroad Generator, which includes a built-in spline component by default for building roads. This flexibility gives us a powerful way to reuse the same PCG setup across different blueprints. The only requirement is that the spline-based actor must have a tag that matches the one specified in the PCG graph. In our example, the tag is street. This tagging allows the PCG system to properly recognize and sample from the spline actor, enabling fully procedural placement of buildings or other elements along any compatible spline-driven blueprint. In our case, we are using the Crossroad Generator because it includes tools that allow us to build complex road structures in just a matter of minutes. We'll take advantage of this and create a simple road layout to demonstrate how PCG can be combined with the building generator to generate a more detailed street or small city environment very efficiently. For this demonstration, we've built a basic road system that simulates a few street blocks or a small town center. Now, let's move forward and show how to utilize PCG with these more complex road layouts. Start by dragging and dropping the PCG graph into the editor and scaling it up so that it fully covers the crossroad and road system we just created. As mentioned earlier, for PCG to recognize which roads should have buildings along them, we need to tag the road blueprint with the same tag we used before, in this case, street. After assigning the tag, PCG knows where to scatter or sample the buildings. You might notice that some buildings are overlapping with the roads. We can fix this easily by adjusting the start offset in the spline sampler node. Setting it to a value like 800 pushes the buildings away from the road edges. One of the biggest advantages of our building generator is its built-in features that allow for extensive randomization and customization of buildings. This flexibility makes it a perfect match for procedural workflows. If you want to fine-tune individual building settings directly from the PCG graph, you'll need to enable template actor editing in the spawn actor node. Once enabled, you gain access to all the parameters inside the building generator. For example, you can go into the main generator settings and change the building layout. When you go back to the editor, the changes are immediately visible across all instances. Any setting you adjust in the building generator will now be reflected in real time through the PCG graph. So for example, if you change the mesh distribution to random, such as on the rooftops, you'll notice the building generator will automatically apply different rooftop variations across all sampled buildings. This is a really powerful approach for quickly introducing visual diversity across the environment, which helps break repetition and make the scene feel more natural and interesting. However, when you change any parameter in the building generator's settings panel, those changes apply globally to all spawned buildings. While that might be fine in some cases, what we'd really like is to have each building at each sample point use a different layout or configuration. To achieve randomized building layouts across sample points, we'll start by introducing a custom attribute. First, we create an instance parameter of type integer and name it random index. This parameter will control the distribution of different building layouts across all sampled buildings, breaking up visual repetition. Since we have 4 layout types, we'll use integer values from 0 to 3. Next, pull the random index into the PCG graph using the getParameter node, and connect it to an addAttribute node, input A. For input B, we create another attribute node and set its default value to 1, then connect it into the add node. This sets us up for applying variation. Temporarily disconnect the transform points node from the spline sampler and insert an attribute noise node. This node will generate random values per point, helping us distribute layout variations procedurally. Let's go ahead and connect the attribute noise node to the spline sampler node first, so the random values can be applied directly to each sampled point. Then, connect the addAttribute node to the max value input of the attribute noise. This helps define the upper limit for our randomization. To inspect what values we're generating, enable debugging on both the attribute noise and addAttribute nodes. Next, specify an output target in the attribute noise node using the internal name of random index, and set the input source to density. This works fine as a default driver. Once those are set, the error message in the node will disappear. You'll see random values being passed through the graph. Because our layout types need whole numbers, we then insert a floor node after the noise output, and set its output target to random index as well. Now, with debugging active on the floor node, you should see clean, randomized integers between 0 and 3 distributed across all sample points. The next step is to add a copy attributes node after the floor node. This node helps us transfer the generated random index values and make them available to the building generator, effectively driving the variation of building layouts per spawn point. Connect the source and target inputs of the copy attributes node to the output of the floor node. Then, reconnect the copy attributes node to the transform points node, maintaining the correct data flow in the graph. Now head over to the spawn actor node. In the actor property override section, add a new array element. This override setup allows us to apply unique settings to each spawned instance based on the PCG data. Set the input source to random index. And for the property target, paste the internal name of the building layout variable from the building generator. This binds the randomized index to the layout parameter for each spawned actor. As a result, you'll now see different building layouts randomly assigned to each sample point, creating a visually rich and varied street or city setup. You can further fine-tune the randomness by adjusting the seed value in the attribute noise node. Changing the seed will regenerate the distribution, allowing for quick iteration and optimization of building placements. Finally, select all the nodes related to this setup in your PCG graph and group them under a comment labeled Random Building Layout for better organization and readability. Now that we've automated the random layout distribution across the spline points, let's take the randomization one step further. When we return to the editor, we notice that all buildings currently have just one floor. To make our cityscape more diverse and visually interesting, let's randomize the number of floors, adding a second floor randomly to some buildings for additional variation. To do this, we'll start by adding a new instance parameter. Create a new integer variable and rename it randomSwitch. Set its default value to 2, which will allow us to generate values 0 or 1, ideal for binary switches like enabling or disabling a second floor. Next, pull this parameter into the PCG graph by typing get randomSwitch. And then copy and paste an existing attribute noise node to reuse it for this logic. Connect the randomSwitch parameter to the max input of the new attribute noise node. In the output target field of this node, paste the internal name of the randomSwitch parameter so it knows where to store the generated values. As before, insert a floor node after the attribute noise node to convert the random float values into whole numbers, 0 or 1, ensuring clean binary decisions. Now, disconnect the transform points and spawn actor nodes from the previous copy attributes node, and instead connect them to a new copy attributes node placed right after the floor node. This makes sure the processed randomSwitch values are passed correctly into the spawning logic. Enable debugging/inspection on these nodes if you'd like to visually confirm the values being generated. This is useful for verifying that you're actually getting a mix of zeros and ones, which will control the floor count. The next step is to add a copy attributes node after the floor node. This node helps us transfer the generated random index values and make them available to the building generator. Don't forget to set the output target of the floor node to randomSwitch as well. Now let's reconnect the transform points nodes to the rest of the logic so everything flows correctly within the PCG graph. Then, go to the spawn actor node and, in the actor property override section, add a new array element. Set the input source to randomSwitch and assign the property target using the internal name of the second floor enabled parameter from the building generator. This step links our newly created randomized switch to the actual functionality that controls whether the second floor is enabled on each building. To keep things organized, group this new section of nodes and label it with a comment like random floor switch. When you return to the editor, you'll notice that some buildings now have only one floor while others include a second floor. Automatically toggled by the PCG system based on the randomSwitch. This approach adds another layer of variety and realism to your procedural city. You can apply the same method to randomize any other parameter inside the building generator, allowing for deep customization and a more visually diverse environment. Now let's scale up the PCG boundaries so we can observe how the system behaves across a larger road network. First, clean up the current PCG layout, then scale the PCG gizmo so it covers the entire road system. If you want buildings to spawn along additional roads, make sure every road has the appropriate tag, specifically, the street tag, assigned. Click on each road to verify the tag. If any are missing it, simply add it. Once all relevant roads are tagged, regenerate the PCG to see the results. You'll notice that buildings are now spawning across the extended road system. However, on closer inspection, especially at intersections or crossroads, you may observe duplicated buildings. This occurs because buildings are being generated on both sides of intersecting roads, leading to overlapping geometry. Additionally, you might notice buildings appearing beneath bridges, which is another issue we need to address. To fix this, head back into the PCG graph. First, temporarily disable the spawn actor node and disconnect it from the transform points node. Then, for each transform points node, add a bound modifier node. In the bound modifier, adjust the mode parameter to set, and define the minimum and maximum bounds to -500 and 500, respectively. Apply these settings consistently to both nodes. Next, enable debugging mode on each node so you can visualize where the points are overlapping. It's crucial that the bound modifier is in set mode. Without it, the debug view won't display the sample points properly. Once you've confirmed the overlapping areas, add a merge points node to combine the outputs into a single stream. Follow that with a collapse points node to remove points that are too close together. Set the distance threshold in the collapse points node to 1500, ensuring that overlapping or nearby points are collapsed into a single one. Finally, reconnect the spawn actor node to the output and review the changes in the editor. You'll see that duplicate buildings at intersections have been removed, and the layout is now cleaner, with no overlapping structures, offering a more efficient and visually consistent result. To address the issue of buildings spawning under bridges, begin by tagging the bridge structures in your scene. Assign a tag such as bridge to these elements so that your PCG system can identify them and prevent overlapping. In the PCG graph, add a getActors data node and set its actor filter to all world actors, then specify the bridge tag to target only those structures. If you have multiple bridges, enable multiple selection to cover all relevant actors. Next, add a bound modifier node after the getActors data node. Set its mode to scale, and configure the minimum and maximum bounds to a value like 10 to slightly expand the bounding area. This ensures the system detects overlaps accurately. When visualized in the editor, you'll notice sample points overlapping with building positions. To remove these conflicting points, introduce a difference node after the collapse points node. Connect this difference node to both the collapsed building points and the processed bridge points. Finally, reconnect the spawn actor node to the output of the difference node. In the editor, you should now see that buildings under bridges have been successfully removed. To further improve the visual variety, you'll want to break the mirrored repetition of buildings on either side of the road. In the PCG graph, duplicate the nodes responsible for randomizing building layouts and floor counts. Also, duplicate the getActor data and spline sampler nodes that feed those systems. Connect this second chain to the transform points nodes that offset buildings on the opposite side of the road. Reconnect the output of this chain to the merge points node to unify everything downstream. Be sure to use different seed values in the duplicated attribute noise nodes to ensure variation between sides. Additionally, tweak the distance increment in the spline sampler node to slightly shift the buildings along the spline, further breaking up symmetry. Once done, return to the editor. You'll notice significantly more diversity in the building placement, enhancing the realism and uniqueness of your procedural city layout. We're just scratching the surface of what's possible with the building generator. The system is incredibly versatile and can be customized far beyond what we've shown so far. With a bit of creativity, you can add random rotation to buildings, randomize materials, and control nearly every element within the building generator to create highly diverse cityscapes. This demonstration is just a small glimpse into its full potential. To wrap up this walkthrough, there's one more powerful integration to explore, and that is Foliage. We've prepared a separate PCG setup focused solely on foliage distribution. Once you drag and drop this Foliage PCG into the editor, the first step is to expand its boundaries so that it covers the entire area alongside the road network. After generating the foliage, you'll notice trees and grass are scattered across the terrain, while roads and crossroads are already excluded from the distribution using tags. However, you'll also observe that the foliage overlaps with buildings. To resolve this, simply open the main blueprint used for all buildings, which is called BP_building generator. In this blueprint, add an actor tag named building. Once this tag is in place, every spawned building in the PCG graph will inherit it. Now, go back to your foliage PCG and regenerate the output. The result, buildings are now excluded from foliage sampling, and everything appears clean and properly aligned. The integration of foliage with the PCG-based building system not only enhances the realism of your procedural environments but also opens the door to creating fully dynamic ecosystems within your urban layouts. By tagging key actors, like buildings, you allow the PCG system to make intelligent decisions during generation. This prevents undesirable overlaps and ensures that vegetation only appears where it makes sense. For a more in-depth look at this process, we highly recommend watching episode 11 of our tutorial series, which is entirely dedicated to PCG foliage setup for Crossroad systems. It's a great resource to get inspired and tailor your procedural environments exactly to your vision. Thank you for watching this 5th episode of our video tutorial series, covering the features of the Building Generator tool. If you're seeking to elevate your environment and create stunning scenes, the Building Generator for Unreal Engine is an indispensable tool. You can find it on the Fab Marketplace, and the link is available in the video description. Thank you for watching, and don't forget to render your tale with us.